Here in this video, I'm going to be reviewing some properties of logarithms. And to start off here, we have our natural log function, and it says that we have the domain is 0 to infinity, and the range is negative infinity to positive infinity. And you can see over here to the right where I have the graph, the viewing window I have is -5 to 5 on the x and on the y-axis. And here we have our graph of our natural log function. And we can clearly see that the domain is 0. It never crosses the y-axis here, so it's going from 0 to infinity. And the range, this graph keeps going down forever, getting ever so close to the y-axis. And it then continues to go up forever, so the range, the y values, would be all real numbers. And number 2 says the function is continuous, and we can tell there's no breaks in the curve. It is continuous. It's also always increasing, okay? And it's also one-to-one. So that means for every x, there's exactly one y value. And of course, we can see the graph is also concave downward. So let's look at kind of an example here. We have an example here. It says find the domain of -2 ln of x. So we want to know what values can x take on. Well, the domain, recall, for the natural log function is 0 to infinity. So that means we cannot take the natural log of 0 or anything less than 0. So that means the x value here has to be what? The x value has to be strictly greater than 0. So this would be our domain. X has to be greater than 0, or we could certainly just say that the domain is 0 to infinity. Either one of these notations would be appropriate, and we use parentheses because x cannot be equal to 0. If it could be 0, we'd use a bracket. All right, what about this next example? We have 8 ln of x minus 15. What is going to be the domain of this function? Well, once again, x minus 15, we're taking the log of the natural log of x minus 15. So this quantity has to be greater than 0. So if we solve for x, we can clearly see then that x has to be greater than 15. So if you plug in 15, we're going to get 0. If you plug anything less than 15, you're going to get a negative number, and we cannot take the natural log of negative numbers or 0, so x has to be greater than 15, or we could say 15 comma infinity. All right, some other properties with your logarithms. Hopefully you recall some of these. The natural log of 1 is equal to 0. Because remember, this is really saying e to the 0 power, e to what power equals 1? Because remember, for your natural log function, that really means log base e. Okay, so this is really saying log base e of 1 equals 0. So this is really implying e raised to the 0 power, and of course anything to the 0 power is 1. Property 2 says that if you have multiplication, the natural log of a times b, we can split that into the natural log of a plus the natural log of b, so we can expand the expression. And if you have natural log of a to the n, if you have an exponent, we can pull the exponent out in front of the natural log. And number 4 says that if we're dividing, we can split that into the natural log of a minus the natural log of b. And a lot of times that's what we want to do. We want to either be able to expand or condense your logarithms. And most of the time here, we're probably going to look at expanding to make our terms a little bit simpler to work with. So how could we expand the natural log of 5xy? Well, all of this is being multiplied, so we could use our property above and we could say, well, the multiplication can be split into addition, so we would have ln of 5 plus the ln of x plus the ln of y. So that's how we could certainly expand the multiplication into addition. The other example we have is the natural log of the square root of x minus 1. Well, we could think of this as the natural log of x minus 1. The square root, we could write that to the 1/2 power. And using the property above, we can take this fractional exponent. The exponent can be pulled out front to 1/2 the natural log of x minus 1. So this is another way we can help expand or rewrite this using our properties above. Okay, so if you need to, make sure you go back and review some of these properties here. You will need to use this a little bit as we go through the chapter. All right, just to review a little bit here, finding the limit of the natural log of 6 minus x as x is approaching 6 from the negative or the left-hand side here, a little 6 to the negative, so we're approaching it from the left. And of course, we can't use really direct substitution because we would have the natural log of 6 minus 6, which would be the natural log of 0, and we cannot do that. So it may be helpful for this example to actually look at the graph of the function. And if we were to graph the function ln of 6 minus x, we're going to find out that the graph would look something like this. Okay, so here's 6. We know we can't get to 6, and the negative is giving us kind of the reflection of our graph. So instead of the graph curving this direction, it's going to be reflected. So it's going to look something like this here. And we can see that it's going to get ever so close to 6, but it's never going to touch or cross 6, because if x becomes 6, we get 0, and if it goes bigger than 6, we get a negative number, and we cannot take the natural log of 0 or negative numbers. So if we look at 6 as we approach this from the left, okay, now, and if you look at this piece, it makes sense that we're approaching only from the one side, because if we can't really approach 6 from the right-hand side because there's no graph over here. So it wouldn't make any sense to approach the graph from the right-hand side anyhow. So as we approach 6 from this side, as we get closer and closer to 6 with our x value, we can follow the graph as we get closer and closer. What are we approaching? Well, what is our y value approaching? Remember, when we're looking for the limit, we're looking for what is our y value approaching. Well, because the graph is constantly going down, our y value is doing what? It's constantly getting smaller. So our limit, we could say, does not exist, or DNE does not exist. And more specifically here, we could actually indicate that it is going to negative infinity. And remember, when we say negative infinity, that's really telling us why the limit does not exist. Negative infinity is not the limit. That is telling us why the limit does not exist. All right, we have another example. We have the limit of the natural log of x divided by the square root of x minus 4. And here we're looking at as x approaches 5 from the right. Now, if we were to look at the graph of this particular function, the graph's going to look like this. 1, 2, 3, 4, go over here to 5. And our graph is going to look like this. It's going to look something like this here, where it's going to get closer and closer here to the x-axis, but it will never cross it. And we would have an asymptote here at 4, because x cannot be equal to 4 because of being in the denominator. We would get 0 in the denominator here. And if we look at approaching 5 from the right, well, we can certainly do that, because here we actually approach 5, and we could go straight across here and figure out what is this y value that we're approaching here. Well, if you look closely here, we could actually use direct substitution, right? We can actually plug 5 in. So we could actually take the natural log of 5 over the square root of 5 minus 4. So don't be misled here with this example. We could actually use direct substitution And we would find that the natural log of this expression would be approximately 1.6. So we could see here that we're going to approach, at this point, a y value of 1.6. So really what I want you to realize from this is to review a little bit of your properties of logarithms, recall the domain and the range of the natural log function, and realize that we cannot take the natural log of 0 or negative numbers. Okay, it has to be greater than 0. And that's why we look at the examples here. We have to set the expression we're taking the natural log of greater than 0, because if it's 0 or less than 0, it's not within the domain. And recall your properties for logarithms on how we can expand or condense your logarithms, because we will use this in the next couple sections here with we start to look at finding the derivatives involving natural logs.